Hello, class. So on this video, we'll continue on section 3.2/4.1. In the previous video, we introduced this notion of what it means for a linear nth order differential equation to be homogeneous. And if you remember, all it was is that whatever is not being multiplied by a derivative, right? So there could be an expression. So for example, the general form for an nth order linear differential equation has this part, g of x, right? Where that's the part that is not being multiplied by any derivative or y. And again, you can think of y as the zeroth derivative of itself, right? And so this doesn't have to be zero, but in the case of a homogeneous differential equation, we force that part that's not being multiplied by any derivative of y to be equal to zero. And that's what it meant to be homogeneous. Right? And then I also noted that we're going to only be working with linear differential equations. So anytime I say a homogeneous differential equation, you have to know that I'm implying that the differential equation is linear. I'm not 100% sure if the homogeneous implies linear all the time in the regular literature. I think it does, but I'm not sure. But for the purposes of this class, if I say a differential equation is homogeneous, I'm also saying it's linear. Okay. So even if I omit the linear part, you have to think, okay, he said homogeneous. I know that the differential equation is linear. And then the last thing we saw was this superposition principle for homogeneous differential equations, which was what I said was kind of crazy because intuitively, just thinking about a differential equation, there's no reason for why it works. But given that we have any number of solutions for a homogeneous differential equation on some interval I, right, so they all have to be solutions on this interval, then any linear combination, remember I said that whenever I say linear combination, think of a sum of the functions with arbitrary constants in front of them. Right? So if I say y is a linear combination of y sub 1, y sub 2, y up to y sub k, think this expression here. Y equals a sum of the functions with arbitrary constants in front. So any solution that looks like this, or any function that looks like this, is also a solution to the differential equation on this interval I. Right? That's what I said was crazy, right? And again, there's no intuitive reason for what that works unless you think of linear algebra behind it. And I mentioned I'm not going to prove this in the lecture. You're going to prove a version of this in the next homework, and it's very easy to see how it works. Okay. Now let's see an example. Okay. So here I'm telling you that y1 equal to x squared and y2 equal to x squared times ln of x are both solutions to x cubed times the third derivative of y minus 2x times y prime plus 4y equals 0. Okay. Now notice that this is a homogeneous differential equation. And again, whenever I say homogeneous, I'm also saying it's linear, right? So you can check that it's linear. Okay. Hence, we know that any linear combination of these two functions, which again is just the sum of them with arbitrary constants in front, is also a solution for this differential equation. Now you have to be careful, right? Because wherever this function y is a solution depends on what interval were the original function's solution. Okay. Now this brings me to the next definition I'm going to give, and then I'm going to go back to this example so we can say, okay, on what interval is any linear combination of these functions also a solution? So I've been talking about this for a little bit now. Now I want to make it formal because now that we're talking about linear independence, this is going to show up a lot. So we've already seen this show up when we're talking about existence and uniqueness theorems. We've seen it show up when we're integrating things. For example, if we're integrating a function, then that function has to be continuous, so that can restrict our interval for which our solution is an actual solution. Right? So to make this more precise, right, given an nth order differential equation, right, not necessarily linear, right? So I mentioned before that an nth order differential equation has this form. And so given an nth order differential equation, not necessarily linear, let y naught or y sub 0 be any solution, right? So any solution to this differential equation. Right? The interval of definition for y naught is the largest, and I put largest in parentheses because I mentioned that in class we always or most of the time, we want to use the largest interval for which this function is a solution. And we saw this in the existence and uniqueness examples that we've done a couple already in class. Right? But in practice, the largest interval might not work, right? Maybe the largest interval is negative infinity to infinity, but the context of the problem, negative numbers don't actually work or make sense. So in that case, your interval could be the interval 0 to infinity. Okay? So the interval of definition for y naught is the largest interval with respect to x for which y naught is a solution. So basically, on what look at your function y naught, and then look, okay, for what values of x is this function a solution? So now we give this interval a precise name, and it's called the interval of definition. Okay? So, for example, let's say you're looking at the differential equation, dy dx equals x to the 1/2 times y to the 1/2. Or actually, let's simplify. Let's just do x to the 1/2 first. Okay. This is separable, right? So we know how to find a solution. Just integrate both sides. And I'm going to skip some steps here. So I'm just going to go directly to the integral. So here we're going to have the integral of just dy. And then on the right-hand side, I'm going to have the integral of x to the 1/2 dx. Okay. Now, just integrate both sides, right? But however, notice that when we integrate, there is some restriction. The function x to the 1/2 is only integrable on whatever interval it is continuous, right? So the fact that we're trying to integrate x to the 1/2 to find a solution already tells you that you have to restrict your interval of definition, which I'm just going to call I, to 0, infinity. Again, because we need our function to be continuous for us to actually integrate it, and x to the 1/2 is only continuous on the interval 0 to infinity. Now notice here that I write I as a not necessarily an open interval. Okay? So this is a thing where it might depend on what book you're using. Since a function, you actually have to differentiate it, right? You actually have to take its derivative. And derivatives only work with open intervals. Most of the time, you're only going to see the interval of definition as being an open interval. Okay? However, in this book, you'll see that the interval of definition is also included as it can also have closed parts, so it can include endpoints. Now, again, it depends on what book you're following, whether you include endpoints or not. If you remember I don't know if it ever came to play, but in the examples when we were looking at the existence and uniqueness theorems, it was potentially possible for the interval in which the solution existed to have some of its endpoints included, right? So for it not to be a necessarily open interval. Okay? I don't know if in the examples it ended up happening that we could have an interval that had a closed part to it, but in this book, they do allow for that, okay? So if you want to include endpoints of intervals as part of the interval definition, since that's how the book does it, then you're more than welcome to do it. I prefer to not include the endpoints because, again, we're assuming that this function is differentiable. You can't differentiate a function on a closed interval because you have to approach the function from both sides, right? So whether you want to include the endpoint or not include an endpoint, that's up to you. Again, I prefer without including the endpoint, but the book includes them, so you can just include it. Right? So going from what the book does, as of now, our interval of definition is already restricted to the interval 0 to infinity, including 0, again, because we have a restriction on x, right? We have to integrate this function. Well, this function is only integrable on the interval 0 to infinity, including 0. Okay. Now, let's just go through the integration. So the integral on the left side becomes, well, y, right? So we're integrating with respect to y, plus a constant. So let me do something here. So y plus a constant equals, here you integrate this, so you use the power rule. So if I do it right, so you add first and then divide, so you get 2/3 x to the 3/2 plus another constant d. Right? Combine the constants and you get your solutions, or the general solution is of the form 2/3 x to the 3/2 plus an arbitrary constant c. And again, I'm just combining d minus c into a new arbitrary constant, which I'm using notation, calling it c again. So for any function here, what's the interval of definition? Well, there's no other restriction involved, right? The only restriction we saw was the fact that we have to be able to integrate this function. So x has to be a non-negative number. And you can see, well, once you find the general solution, you also have to check, okay, is there something here that doesn't work? Well, there's nothing here that doesn't work, which already doesn't work, right? When you look at this function, what's the domain of this function? Well, it's all numbers greater than or equal to 0. Okay? So there's no new restriction there. So the interval of definition for any function that looks like this, so for any solution where you replace c by any constant, right, is 0 to infinity. And again, in the book, they include the endpoint. Now, in the homework, I'm now going to be asking you to actually include the interval of definition, because I'm going to ask you to write, if you find a solution, I want you to tell me on what interval does this solution work. Okay? Let's do one more example of something tricky that happens. So let me do, so this is going to help you a little bit in the homework, which is fine. I don't mind that this helps you to do the homework that's due tomorrow or today if you're watching the videos on Friday. So suppose now I'm looking at the differential equation, dy dx equals y to the 1/2 x to the 1/2. And I want to find solutions and give what the interval of definition is for each solution. Well, actually, let's simplify. No, let's leave it like this. Do it a little bit different to what's in the homework. Well, this differential equation is separable. Right? So just divide y to the 1/2 on both sides. Right? So we get dy dx over y to the 1/2 equals x to the 1/2, and then we're going to integrate, right, with respect to x. Now, okay, so actually let me write the integral, and then I'm going to say what I want to say. Now notice that at the right-hand side, we have the same restriction as always, as in the previous example. We're trying to integrate x to the 1/2. For us to integrate this function, it has to be continuous. So we're already restricting the interval of definition I to the x value 0 to infinity. Now, notice that something happens on the left-hand side. We are dividing by y to the 1/2. So in a sense, this is also restricting not the domain of our solution, but the y values of our solutions, basically the range of our functions. So what's happening here is you're kind of seeing something that is telling you that, okay, I'm dividing by y to the 1/2. Okay, that's telling me that y has to be greater than 0, right? I can't plug in 0 because if I plug in 0, I'm dividing by 0. And I can't plug in negative numbers, so I can't take the square root of a negative number in the real numbers. So here I have an asterisk. I'm going to leave it as an asterisk for now, where I have this condition. Okay, the range of my functions have to be y greater than 0. Okay? So I'm going to leave that as an asterisk, and I'm going to talk about that later. So let's integrate both sides. See what we get on the left-hand side. So I think on the left-hand side, I get 1/2 y to the 1/2, right, plus a constant. On the right-hand side, we already know what we get. We get 2/3 x to the 3/2 plus another constant. Now, I'm going to combine both constants here. So I'm trying to solve for y. So move c to the other side, write d minus c as a new constant c. Right, so I get 2/3 x to the 3/2 plus c. I'm going to multiply both sides by 2, right, to get rid of the 1/2. And I get y to the 1/2 equals, so multiply by 2, 4/3 x to the 3/2. C is an arbitrary constant, right? So when you multiply an arbitrary constant by 2, it's still an arbitrary constant, so let's call it c. Finally, I'm going to take the square root of both sides. The square root of a variable is always the absolute value. And here I'm going to get the square root of 4/3 x to the 3/2 plus c. I get rid of the plus or minus of the absolute value by putting plus or minus on the other side, and I get that my general solution has this form. Okay, now we already knew that the interval of definition was already restricted to the interval 0 to infinity. However, notice that now something happens. Depending on what your value of c is, now you have another restriction. Why? Because now you have the restriction that whatever's inside the parenthesis, the square root here, has to be greater than or equal to 0. So you also have the restriction that you're still taking a square root here, but we already took care of that with this restriction here because it's the same restriction, right? Basically, you can't integrate the square root function unless it's continuous, and of course, that interval also corresponds to the domain of this function. Okay. So we add this new restriction on I, and this restriction is going to change depending on what you choose for C. Okay. So for example, let me do it here on the other side. If C equals 0, we get the solution y0 equals, and let's take the positive one. And I actually have to talk about that because I have another restriction here. So actually, let me, because I said that you can leave the solutions as plus or minus. So let me, before I say this, there is another restriction here. I'm going to get to the asterisk part in a moment. Instead, I'm going to go back to the original one. So in the original differential equation, what do I have here? Well, I have that I'm taking the square root of y. So this also restricts y. It's a smaller condition than this one, but it's telling you that y has to be greater than or equal to 0. Now that is something that you have to be careful of because, well, when you look at this thing here, you can't take the minus part because if you take the minus part, you're going to get y having negative values. From above, we know that that is not possible. So in fact, you can't even take the negative part there. You can only take the positive part. Okay, so if I plug in c equals 0 for my constant, then I get a solution, y0 equals 4/3 x to the 3/2, right? And in this case, for this one, the interval of definition is then just 0 to infinity as we had before. What happens though if we do something else? Let's say that instead I choose c to be a constant. Say c equals 5. Let's do 4. So c equals 4. So I'm trying to choose something that's going to be nice later. So if I choose c to be 4, and I call this solution y1. Oh, and I needed a square root here, sorry. So I write y1, right, with c equals 4. So now I get a solution, 4/3 x to the 3/2 plus 4. And of course, the square root of that. Now, what's the interval of definition for this? Okay. So we already know that we need I to be the interval 0 to infinity, including 0. But again, the fact that we're taking the square root of this introduces a new restriction. So basically, the fact that the domain of this function could be something bigger than this also gives you restrictions, right? Or something smaller. So let's say we solve, right? Because we need that to be greater than or equal to 0. So basically, we need 4/3 to 3 halves plus 4 to be greater than or equal to 0. Subtract 4 to both sides. 4/3 x to the 3 halves is greater than or equal to -4. Multiply both sides by 3, divide by 4. X to the 3 halves is greater than or equal to 3, okay? -3. Now, you look at this here and you think, what x values work for this? Now, it turns out that in this case, if you look at this here, it turns out that if you want x to the 3 halves to be greater than or equal to -3, again, you get I to be, I to be 0 to infinity, right? Because those are the x values that work for this inequality. Now, what if instead, let me do one more example, and then I'm going to talk about this asterisk here that I wanted to mention. So let's do y2, where now we're going to choose the constant to be not 4, but -4. Right? So our solution then is, and again, we can't use the negative part because we know that y has to be greater than or equal to 0 from the original differential equation. Okay. So instead, I use the positive part. So I get the square root of 4/3 x to the 3 halves, now -4. Again, I need the inside of this to be greater than or equal to 0, just for this function to be defined. So that is also, as I mentioned, that might also affect the interval of definition. All right, so let's solve this. 4/3 x to the 3 halves -4 is greater than or equal to 0. I'm going to simplify a little bit. Oh, 3 halves, sorry. So I'm going to simplify a little bit here. So skip some steps. I get x to the 3 halves is greater than or equal to 3. Now, you take 2/3 of both sides, and you get that x has to be greater than or equal to 3 to the 2/3, which is what? You're squaring 3, taking its cube root. So the cube root of 9. Now, notice that the cube root of 9 is bigger than 0. So the fact that the domain of this function is x greater than or equal to the cube root of 9 restricts your interval of definition. So for this function, I is in fact a smaller interval than the previous one. Right? We can't include anything less than the cube root of 9. Right? So just an example of things that could affect your interval of definition. Anytime you're integrating an expression involving x, that can affect your interval of definition. Right? Anytime you get a function, depending on whatever constant you choose, the domain of that function can affect your interval of definition. Okay? Now let me talk about this asterisk here. So from the original differential equation, we knew that we had to take y to be greater than or equal to 0. Meaning that solutions of this form, where we had the plus or minus here, wouldn't even work with the minus part. However, we also had the restriction from integrating y, that y was greater than 0. Is that going to be a problem for us? Well, it turns out that that restriction is not a problem for us. Why? Because even though y has to be greater than 0 for us to integrate it, when we look at the actual differential equation, y can be equal to 0. And in fact, the solutions we get after integrating both sides, for example, look at this solution, y naught. There, the x could be 0, for which case y not equals 0. And even though when we're integrating y, we're saying that y can't be equal to 0, you can plug in this function here, and you'll see that it is a solution even if x equals 0. What does that mean? That means that in a sense, the original differential equation, the conditions that we get there kind of trump conditions that we get on y by integrating. So even though in this case, for us to actually integrate y has to be greater than 0, the fact that in the original differential equation, that condition is not there, like y can actually be 0, and the fact that the solutions we get after integrating do include functions for which y equals 0, that trumps the fact that y has to be greater than 0 to integrate. So in a sense, the interval of definition for x trumps what happens with y. Right? So the only condition you have to worry about for y is, are there any conditions that matter when I plug in y as a function into the differential equation? The conditions you get here, like, oh, y has to be greater than 0 for it to integrate, okay, that's true, but after you integrate, you get solutions for which y equals 0 work. So there's no reason for you to not include those solutions, right? So there's no reason for me to say, I'm not going to include the solution y not because it includes x equals 0, right? There's no reason for me not to do that. Because again, you can verify that if you plug it in, it works with x equals 0. So in summary, when you're doing or trying to find the general solution for a differential equation like this, the things that matter are any conditions on your function originally on the differential equation, any conditions on your independent variable originally on the differential equation, any conditions you get on your independent variable because of integration, and any domain restrictions you have on your solutions. And this is an example that I work. This basically is going to take care of any example you see in the notes or in the homework in terms of what the intro of definition can be. The only thing we're going to add, well, we're going to add something. So we're going to, because linear independence is going to play a role here. But in terms of given a differential equation and you trying to find the general solution like this, the only thing that matters are those 4 things that I said. Again, some subtleties do arise when you're trying to, for example, integrate y to the 1/2, to the negative 1/2. However, again, the interval of definition kind of trumps those asterisk conditions that arise. So don't worry about those. If you have a general solution, look at that. And if the interval of definition works for these general solutions, don't worry about that as long as they also work for the original differential equation. So that's my spiel on the interval of definition. It's something important because you don't want to work with solutions where they don't even exist or don't make sense for them to exist in the context of your problem.